This is the third empirical formula calculations video, and in this particular video we're going to look at how to calculate an empirical formula when you have two different samples. Now, because we're going to try and calculate an empirical formula with two different sample sizes, you are going to have to always find the percentage of the element within the compound. That is the only way that you'll be able to adjust for the fact that you've got two different size samples, because the percentage will never change on a compound. Then you'll go through the standard procedure for calculating an empirical formula. You'll create a table, you'll find the moles, you divide the simplest ratio, determine the empirical formula, calculate the molar mass, determine the molecular formula, and then draw any structures that you're required. So let's look at an example. Aspartame is a compound used as an artificial sweetener in foods and beverages. It contains the elements carbon, hydrogen, oxygen, and nitrogen. A 7.35 gram sample was completely burnt, resulting in carbon dioxide and water, which were collected and found to weigh 15.36 grams and 4.041 grams respectively. Now, a second size sample. Please note that the second size sample is different from the first. This means we're going to have to find the percentage by mass of each element within the compound. So the second sample of aspartame was treated to convert the nitrogen to ammonia, and the resulting ammonia was absorbed in 100 ml of 0.3559 molar hydrochloric acid. The excess hydrochloric acid was titrated to equivalence point using 28.18 ml. So this here is using a back titration in order to calculate it. Another 1.5 gram sample was vaporized at 200 degrees Celsius and 120 kilopascals and found to occupy 0.1972. So this section here is how you're going to work out your empirical formula, and this section here is how you're going to work out your molecular formula. Now let's just look at the section that allows us to determine the empirical formula. So it's telling us that it's got carbon, hydrogen, oxygen, and nitrogen. A 7.335 gram sample was burnt in oxygen. So this means it's undergoing a combustion reaction. And the resulting carbon dioxide was collected and found to weigh 15.36 grams and 4.04 grams of water. Now this section here is going to allow us to find the percentage of carbon present and the percentage of hydrogen. Now the second sample, which was a different size, allows us to convert the nitrogen into ammonia, and then we're going to do a back titration. And this will allow us to determine the percentage of nitrogen and the percentage of oxygen. So I've divided the problem up into the two different samples. So our 7.355 grams sample, CXHYOZNA plus oxygen will give us the carbon dioxide plus water plus the nitrogen product. So we had a 7.335 gram sample, and it gave us 15.36 grams and 4.041 grams. So we're now going to find the number of moles of carbon dioxide. So the number of moles of carbon dioxide is equal to a mass over a formula mass, which is 15.36 divided by 44.01, and this will come out to 0.3490 moles. Now this will give the same number of moles of carbon, and from there we can find the mass of carbon. So the mass of carbon will equal number of moles times formula mass, which is 0.3490 times 12.01, and this will come out to be 4.192 grams. Now, to find the percentage of carbon, we're going to go the percentage of carbon will equal the mass of carbon, which is 4.192, divided by the mass of the sample, which is 7.335, times 100, and this comes out to be equal to 57.15%. Now let's do the same for the water. We're going to find the number of moles of water is equal to a mass over a formula mass, which equals 4.041 divided by 18.016, which comes out to be 0.2243 moles. Now you can see here there are twice as many hydrogens as there are waters, so the number of moles of hydrogen will equal 2 times 0.2243, which equals 0.4486 moles. Now from there we can find the mass of hydrogen, which will equal number of moles times formula mass, which is 0.4486 times 1.008, which comes out to a mass of 0.4522 grams. Here we can now find the percentage of hydrogen, which is going to be equal to the mass of hydrogen, 0.4522, divided by the mass of the sample, which is 7.335 times 100, which will equal 6.165%. So in our second part of the empirical formula, we're using a different size sample, and we're going to be using a back titration in order to determine the mass of nitrogen and hence the percentage of nitrogen. So let's get started. We have a 100 ml sample of hydrochloric, which has a 0.3559 molar concentration, and we bubble our ammonia through it. So the ammonia is going to react with the hydrogen ions to give us ammonium ions. So this is our equation number 1. In the second part, we now titrate our excess hydrogen ions with sodium hydroxide, which has a concentration of 0.1249 molar, and we use a titer of 28.18 mil against our excess hydrogen ions. Our second equation is hydrogen ions plus hydroxide ions gives water. Now, the number of moles of hydrochloric at the start equals number of moles of hydrogen ions, which is equal to CV. So in this case, 0.3559 times 0.1 will equal 3.559 times 10 to the negative 2 moles. Over here, the number of moles of sodium hydroxide equals number of moles of hydroxides, which equals CV, and this will equal 0.1249 times 0.02818 litre, and this will come out to be 3.52 by 10 to the negative 3 moles. This in turn will equal the number of moles of hydrogen ions which are in excess. And please make sure you state it so that your marker is your friend. This means now that you can now work out the number of moles of hydrogen ions from reaction 1 that we used, which will equal number of moles of hydrogen ions from the start minus the number of moles of hydrogen ions in excess, which will equal 3.559 times 10 to the negative 2 minus 3.52 by 10 to the negative 3. And this in turn comes out to 3.207 by 10 to the negative 2 moles. Now looking at reaction 1, you can see that 1 mole of hydrogen ions reacts with 1 mole of ammonia. So the number of moles of ammonia used will be the same. So the number of moles of nitrogen will also be the same. And from here we'll be able to determine the percentage. Now let's continue on with this particular problem. We've now got the number of moles of nitrogen, so from here we're going to find the mass of nitrogen. And remember, the mass of nitrogen will equal the number of moles times the formula mass, which is 3.207 by 10 to the negative 2 times 14.01. And we have now determined that the mass of nitrogen is 0.4493 grams. So now we can find the percentage of nitrogen, which will be the mass, 0.4493, divided by the sample size, which is 4.719 times 100, and the percentage of nitrogen comes out to 9.521%. Now, in order to find the percentage of oxygen, we need to do it through subtraction. So the percentage of oxygen will equal 100 minus the percentage of carbon minus the percentage of hydrogen minus the percentage of nitrogen. So in this case it will be equal to 100 minus 57.15 minus 6.165 minus 9.521. So this comes out to 27.17%. And we're now ready to do the empirical formula. So now let's set up our empirical formula. So we've got carbon, hydrogen, nitrogen and oxygen. And we have our mass out of 100, which is 57.15, 6.165, 9.521 and 27.17. Now we need to convert these to moles, and remember, to find a mole we go number of moles equals mass over formula mass. So we're going to divide by the formula mass of each element, 12.01, 1.008, 14.01 and 16. This will allow us to find the moles, and the moles in this case is 4.758, 6.116, 1.698 and 0.6796. Now we need to get the simplest ratio, and to do that, remember, we always divide by the smallest. In this case the smallest is the oxygen, which is 0.6796. So the simplest ratio will equal 7.001, 8.999, 2.499 and 1.00. Well, that's not very simple because this is 2.5, so we're going to times everything by 2 and it will come out to 14 18, 5 and 2. So the empirical formula is C14, H18, N5, O2. Now in the second part of the empirical formula, you're going to determine the molecular formula. We have a 1.5 gram sample being vaporized to occupy this volume. So we need to find a mole, so we're going to use PV equals nRT. The pressure was 120, the volume was 0.1972, the number of moles we don't know, the gas constant's 8.314, and the temperature is going to be 200, so temperature equals 200 at 273.15, which is 473.15 Kelvin. So from this I can calculate that the number of moles comes out to 6.0156 by 10 to the negative 3 moles. Now that moles corresponds to that mass, so the number of moles equals mass over formula mass, and this will equal, the formula mass will equal 1.5, which is the mass, divided by the number of moles, 6.0156 by 10 to the negative 3. And this comes out to 249.4 grams per mole. Now we need to do the ratio, which is always equal to the formula mass over the empirical formula mass, and this comes out to 249.4 divided by 249.4, which equals 1. So the molecular formula of aspartame is going to be C14, N18, N2O5. I would like you to try one yourself. So in our empirical formula calculations number 1, question 11 has 2 different sample sizes.